second honors thesis is Josh Mendez, and I'll give him the floor now.
Thank you very much. Greetings. It's a pleasure to be here. I'm Joshua Mendez, ECE, senior graduate, obviously, also in the Earth Science department, and I'm here to talk to you a little bit of the research I've been doing for about a year now, under the direction of Professor Paul Hall in the Earth Science department and advised by Professor Mark Borenstein here in the ECE department. The research has to do with several of the processes that happen inside our planet. These processes are of fundamental importance not only to the way our planet is conformed physically today, but also have huge impacts on the way life developed on this planet over the Earth's history, and as well they have large societal effects too. Now you might be asking yourself, well, why is there a geology kit here, talking about rocks during ECE day? I'm just sort of having this presentation as an example as to how pervasive electrical and computer engineering is, and how it extends to a large array of fields, and how I can bring these two fields, which I really enjoy participating in, how I can bring them together in a project like this. So just before we get into the technical details of the actual engineering project, I'd like to give you a little bit of a geological background. So I'm going to pass a rock around for a minute. I'll explain what it is in a minute. I'll pass it around. So as you know from 8th grade, Earth Science classes, the Earth is conformed by multiple layers. The outermost one being the crust, which is conformed of multiple plates that move and interact with each other. Under the oceans, the crust is about 5 kilometers thick, while under the continents, about 40 kilometers thick in places like the Himalayas, where you get these huge mountain ranges. Now, beneath the crust, you get the mantle. And the mantle, unlike what most people think, isn't a liquid. It's actually a solid. The rock I'm passing around is a green rock. It's called peridotite. It's mostly composed of the mineral olivine. 70% of the Earth is actually composed of this green rock. It seems kind of fitting a green mineral for a green planet. But these rocks, due to their high temperatures, do not deform brittly, they deform ductily. So over millions of years, they can be modeled as fluids. Inside of the mantle, we have the liquid core. That is a liquid. And beneath that, we have the solid iron core, nickel core. So just as a cup of coffee on a table, the Earth has to get rid of heat in some manner, and it does so convectively, where you have hot material rising from the core mantle boundary right here. It rises because it's less dense, releases its energy at the surface in the form of volcanic eruptions, earthquakes like the one we had in Japan a month ago or so. And once it cools, it heads back down, and the process is repeated, a continuous process to form these convective cells inside the mantle of the planet. It takes several million years for a complete process to happen, but they do occur. And these large mantle flows affect what happened on the surface of the planet as well. So as you can see in this simplified diagram, subduction zones, places where two plates come together, are usually resulting in one plate diving or subducting beneath another one, as seen here, coincide with these downwelling portions of the convective cell. Conversely, at locations where you have upwelling, new crustal material is created and the plates move apart. These are called divergent boundaries, or mid-oceanic ridges. They usually happen in the middle of oceans like the Pacific or the Atlantic. Now, at these locations where we get a volcanic activity, about 10% of the volcanic activity that occurs every year, the volatile magma that's erupted every year, occurs at subduction zones. These are your classical volcanoes, volcanoes that permeate human history and that are known for their destructive power, or also biblical references, etc. Volcanoes like Mount St. Helens, Krakatau, and Santorini. About 80% of all the magma or lava that is erupted at the surface of the planet happens at divergent boundaries, where the plates move apart in mid-oceanic ridges. This is a plot which shows the age of a lithosphere as a function of distance from a mid-oceanic ridge. So for example, you can see the Pacific plate or the Pacific Ocean is rapidly moving apart away from this ridge, while the Atlantic one, it is moving apart, but it's doing so at a much slower rate. So that accounts for about 90% of all the volcanic activity that happens on the surface of the Earth. So what happens to the extra 10%? Well, the extra 10% occurs at locations which are known as hotspots. And these hotspots can occur at hundreds, thousands of miles away from any sort of plate boundary, and at first glance seem to be related to the large convective flows that happen inside a planet. In 1971, a geophysicist, Jason Morgan, proposed that hotspots, the surfaced expressions of what are known as mantle plumes, thin upwellings, well, thin, they can be several kilometers in diameter, but thin upwellings that occur from the core mantle boundary and rise passively through the mantle. So the way in this image here on to the left, we see how a plume develops. It starts as an instability at the core mantle boundary. Once there's sufficient material there, it'll rise buoyantly through the mantle, just like the mushroom cloud in a nuclear explosion rises through the atmosphere. When the large head impinges the bottom of the lithosphere, the crust, huge melting occurs. It expels kilometers and square kilometers of magma at the surface and form what are known as large igneous provinces. There are several of these provinces in India, in Siberia. The Columbia River Basin is one of these provinces. And the funny thing to notice is that if we date these the rocks in these large igneous provinces and match them to when a large extinction event occurred. For example, the Permian, the largest extinction event in the history of the planet, where about 60 to 80% of all life was extinguished on Earth. It matches very closely with an eruption in Siberia, with the North Siberian traps. Similarly, if we look at the extinction event at the end of the Cretaceous, when the dinosaurs were decimated, it coincides very nicely with an eruption in India. So once that plume head has been erupted, the plume conduit itself is much smaller. Material still rises through it, but it does so in a much smaller volume flux. And what essentially happens is, if you imagine it to be some sort of pipe where you're pumping magma up through the mantle into the crust, you essentially form a volcano. You'll melt the crust at that point and form a volcano. However, since the plates are moving, eventually that volcano will move off the location of the hotspot, and you'll create a new volcano. That one will also move away from the location of the plume, and you'll get a chain of age-progressive volcanoes, as shown in this diagram here. Typically, these plume structures are maintained to be fixed by the geophysics community, meaning they don't move. They're fixed relative to the core mantle boundary of the Earth. One of the most striking examples, and perhaps well-known, most studied examples of a hotspot track where you get these age-progressive track volcanoes is the Hawaiian Upper Seamount chain that extends from the Kamchatka Peninsula in Russia all the way to the modern-day large island of Hawaii, where we believe the plume is right now. So these are older islands, and these are newer islands. One of the things you notice right away when looking at this is you have this big bend here in the middle that separates the north-south Emperor portion from the east-west Hawaiian portion. Typically, this bend has been explained by a change in plate motion around 50 million years ago, when the Pacific plate changed from going northward to going westward. This is a possible explanation. We have evidence that plates do change and shift around a bit. However, there are several problems with this theory. One of the largest ones is that you look at other hotspot tracks in the Pacific Basin, you notice they are not characterized by such a distinct bend. For an example, this is Samoa, slightly to the south. Furthermore, if you reconstruct plate motions in Australia, the Indian plate, they don't quite explain how the Pacific plate could have shifted almost 90 degrees about 50 million years ago. One last piece of evidence comes from the data provided to us by our magnetic field, the planet's magnetic field. So when a lava is erupted, it's very hot, and as it cools, it'll pass through what is known as Curry temperatures, in which particles inside the melt will align with an external field. We can approximate the Earth's magnetic field as a dipole, meaning that field lines at the South Pole are leaving the planet's surface or pointing straight away from the planet. At the northern pole, they're pointing directly downwards, and about the equators, they're pointing roughly parallel to the surface of the Earth in a northward direction. Here in Boston, magnetic field lines make an angle of about 50 degrees with the surface of the planet. So this can help us tell us a little bit about where a lava or a melt is erupted. If a volcano erupts near the equator, its inclination or the magnetic signatures inside its rock particles will have an inclination of about 0 degrees, meaning it's parallel to the surface of the Earth. So even if that volcano moves away from that location due to plate tectonics or some other geophysical mechanism, this information is preserved, as can be shown in this picture. When the lava is hot, there is no net magnetic field because all the magnetic particles are pointing every which way, and as it cools, they align, and you get your paleomagnetic signature. So now, if we assume a hotspot is a fixed structure inside the mantle, meaning it doesn't move, and the only thing that moves above it are the plates, then all the lavas erupted along a hotspot track should be characterized by the same paleomagnetic signature. And that is true pretty much for the Hawaiian portion of the hotspot track. But it is not true for the Emperor portion of the hotspot track. We see decreasing paleomagnetic signatures with decreasing latitude in this section, meaning that whatever produced this section of the Emperor seamount chain was rapidly moving south during the period prior to 50 million years before present. If we accept the Plume theory, we must remember Plume theories are about 40 years old, it's a fairly new theory. If we accept that's true, then plumes aren't a fixed structure in the mantle, and they can move within the mantle by some process. So in 2009, John Carduno proposed that a plume might be diverted or deflected by one of these divergent boundaries, a location where plates are moving apart. These divergent boundaries can move as well, and don't move over the surface. So his theory is that a divergent boundary passed over the Hawaiian plume because it's a low pressure system, captured the plume, dragged it with it for several hundred of kilometers, at which point the system became unstable. The plume is released and snaps back to its vertical location about 19 degrees north, where it is today. So this snapback motion would be the creation of the Emperor portion of the seamount chain, and finally the Hawaiian portion is just caused by plate motion as the Pacific plate moves east, or westward, I'm sorry. So the question is, can we explore this idea inside a laboratory experiment? And the question is yes. Analog models have been used many times in the past to try to explain physical phenomena inside the Earth and inside the atmosphere and other locations of the Earth. They can be done by using scaling parameters in which you take parameters such as temperature, length scales, velocities, and scale them to a much smaller scale inside your laboratory. While the results of an analog model may not be completely analogous to the phenomena inside the mantle, they can maybe provide directions for more complex numerical models using COMSOL or SITCOM or some other form of numerical analysis program. And they do have one advantage over computer simulations in that they are inherently three-dimensional, and they represent physical parameters. So the way we do the scaling is using two magic numbers, the Peclet number and the Rayleigh number. The Peclet number is used to scale velocities and distances, while the Rayleigh number is used to scale temperatures. And it isn't anything new. Here we have two postdocs, for example, Adrian Lenardic and Helge Gornemann at Berkeley University under the direction of Michael Mango, perhaps the most famous volcanologist alive today, in which they're filling a 2 by 2 meter tank with corn syrup, high fructose corn syrup. It turns out corn syrup is a very good analogous fluid to the rocks in the mantle because it's highly temperature dependent. So Michael Mango usually has an 18-wheeler pull up to the back of the Earth Science department. They use a huge hose to fill up the tank, and the cops aren't usually very happy about that. So for this experiment, however, we needed to create a tank apparatus that was slightly different. Nobody has ever made a tank apparatus that has a moving ridge in it. Plume experiments have been done, and fixed ridges have been done, but not a moving ridge. So these are some of the most important requirements for the project itself. Recreate plate motions as well as ridge motions in accordance to the Peclet number. Recreate a mantle plume in accordance to the Rayleigh number. Automate and monitor plume temperature and ridge motions. And visually record what happens inside the tank. Visually record the interactions between the plume and ridge. So this is a conceptual model. What we added to a model that was at URI, we took one of their ideas and modified it to allow for the mid-oceanic ridge to move. So So what we have here is a tank about 1 meter by 5 by 70 centimeters filled with corn syrup, in which we drag 2 mylar sheets in opposite directions to simulate plate motions. This blue rectangle here is a car which rests on a Acme thread and is allowed to move over the entire surface of the tank and recreates the migrating oceanic ridge. The plume is created at the bottom of the tank and can be created in a number of ways, which I'll get into in a little bit. And we finally visualize what happens inside the tank by shooting a sheet laser through the tank, which will give us a cross-section of the plume as it upwells and interacts with the plates and the ridge. This is the completed SolidWorks model of the tank. It was completed last year, in which we see the tank and the apparatus on top. These provide slightly better images of what the tank looked like before its construction, and the apparatus. Again, we see the ridge, the drive, and the 2 motors, which are actually windshield wiper motors. They were cheap and high torque that we could use to make the plates move. And the top view, which shows the plume source. So this is the completed apparatus once it was finished in November last year. It's in the Earth Science Department. Feel free to stop by if you'd like to see it. It's made out of aluminum for the most part, and the tank is made out of a 2-inch clear Lexan. All the drives use encoders to measure the speed at which the motors rotate. So we have a program, an algorithm, in which a user can set the desired plate velocity, the desired ridge velocity, and the movement is measured using these quadrature encoders. It's sent to the computer. It's compared using a proportional integral derivative method, and then corrections are made to ensure that the plate motions and ridge motions are what the user actually wants. Here's a small electrical block diagram of what the circuitry for the control circuitry for the apparatus looks like. We have a microcontroller, which is it's an Arduino Mega, which provides a lot of user inputs and analog outputs and inputs for this project. We have a driver board that drives the plume, the ridge motors, and the plate motors. As well, we have a thermocouple acquisition device, conditioning device, to measure temperature at different locations inside the tank. And finally, we have an encoder board, which does some of the initial processing when counting the pulses from the encoder. We've also implemented a set of safety inhibits to prevent the user from driving the ridge into the side of the tank accidentally, so that shuts off if the ridge passes a certain point along its path on the Acme thread. And finally, the laser. So here's a CAD image of one of the boards, the driver boards, four-layer driver boards that is used to drive the 3 motors and the puck heater for the plume. Here are the completed electronics encased. We use the power supply, which is courtesy from Professor Mark Ornstein, and a small modified computer power supply to provide 3 volts. This is the user interface. The user interface is written in LabVIEW. It does the initial scaling using Peclet and Rayleigh numbers, and also it provides the user a way to visualize what is happening inside the tank. So there are 2 ways to create a plume. The first one is to inject preheated syrup laced with particles. These can be bubbles, neutral density Dahlgren beads, or even fish scales into the tank. And by shooting the laser, you reflect them off these particles, and you can visualize it with a high-speed camera. This has problems in that it's very hard to get the pressure at the end of the conduit at the bottom of the tank to equal the pressure, the hydrostatic pressure at the bottom of the tank. If you over exceed that, that will overdrive the system, and your data is useless, basically. It's also very difficult to control temperature. So a second method we use is using a Peltier unit, which is basically a heat pump, which can be controlled using PWM, and it's much easier to control using a thermocouple than a closed-loop control system. So here are some of the preliminary results we have when creating a plume. The first one is a plume created with the injection, using a red laser, and the second one is using the Peltier heater. Now, we visualize the plume itself by lacing the entire tank with what are called thermochromatic liquid crystals, which are crystals that will reflect different wavelengths at different temperatures. And here we're shooting with a green laser. We're planning to putting a second red laser on the tank, which will provide a second isotherm around the green an isotherm, and by measuring the distance between red and green isotherms, we'll be able to measure temperature gradients as well. So just to give you a brief idea of some of the results we got, I would like to show you a small video. Of an initial experiment we had that was presented last December at the American Geological Union meeting. So at the beginning of the video, we see a plume forming, thermal instability. When it gains sufficient mass, it'll start to rise buoyantly. The ridge is indicated by the green LEDs. So we see the head rise. It'll impact the lithosphere, at which point we start the plates running. The plume is sheared, and as the ridge approaches, the plume is sucked up into the ridge and follows the ridge for for a good distance before it's spat out the other side. This is a very preliminary experiment. We're still working out some of the kinks in the apparatus, but hopefully this summer we'll be able to run a large number of experiments now that the entire setup is correctly established. And so that ends my presentation. I'd like to make a few acknowledgments to some of the people that helped me during this presentation, especially Professor Horenstein and Professor Paul Hall, as well as other people in other departments. Thank you very much. Do you have any questions? Yeah.
On the front and the back of the tank, you have a no-slip boundary condition. How does that come into the design of the shape of the tank?
Right, so there is a boundary condition. That's actually one of the things we're looking at, because you get return flows, essentially, from the plates moving.
Right.
So if you let the experiment run too long, then you have these return flows will affect your experiment. So right now we're constructing a longer tank that will hopefully get rid of these layers and essentially act as an open boundary. The front part of the tank are sufficiently far away from the plates themselves that they do not affect the experiment itself.
Thank you.
Yep. Yeah.
How do you determine how hot the heater has to be to create a plume that is representative of what actually occurs?
So you do that with the Rayleigh number. The Rayleigh number is a dimensionless number. So essentially, if you can find values for these guys, viscosity, thermal diffusivity, velocity inside the mantle, and you can come up with a dimensionless number, Rayleigh number, and you can match that number inside your tank experiment. You're essentially scaling that to what happens in the mantle. For example, we have a thermal the thermal contrast is about 20 degrees, so our tank is at room temperature and the plume is about 45 degrees. Yep. Any other questions? Yeah.
Do you have any other areas of the globe that would give you experimental data beyond the?
Unfortunately not. Hawaii is one of those cases where it's the only place that has that sort of a morphology, and we cannot find any other places on the surface of the earth that has one of those. Unfortunately, the paleomag data is also fairly sketchy. It's someone else needs to go and get some better data. That's one of the largest criticisms to this theory of plume snapback and plume motion is that the paleomagnetic data is not very well constrained. So even though we